Milk begins as sunlight, grass, and water gathered inside a living animal. Across the world, it pours from cows, goats, sheep, camels, and buffalo. Within that white river lies lactose, the quiet sugar unique to milk. For newborn mammals, lactose is a bright store of energy during helpless beginnings. But each lactose molecule arrives as two smaller sugars joined by one stubborn bond. To the body, that tiny bond can be a locked gate. Without the right key, sweetness passes onward, untouched, and sometimes troublesome. In many adults, the key grows scarce after childhood has quietly passed. Then milk can bring pressure, motion, and discomfort instead of simple nourishment. This human problem is ancient, but nature solved it long before us. In the small intestine, infant mammals make lactase along delicate living folds. The enzyme waits there, meeting milk at the very edge of digestion. Calves, kittens, and human babies all depend on this quiet molecular craft. Microbes learned the craft too, wherever milk sugar entered their world. Some yeasts and bacteria turned lactose into food, breath, growth, and acid. Their hidden chemistry would later guide dairy science into a new industrial age. Long before enzymes had names, milk sugar caught the eyes of physicians. In 17th-century laboratories, whey was boiled until pale crystals appeared. By the 18th century, chemists recognized lactose as milk's own sugar. Yet recognizing the sugar did not explain why some bodies used it easily. The 19th century brought a new idea. Living ferments could transform food. Microscopes revealed yeasts, bacteria, and tissues alive with unseen labor. Scientists watched starches and sugars change, as if guided by invisible hands. Those hands would soon receive a name: enzymes, the workers within life. Lactase entered this story through milk-fermenting microbes in the late 1800s. In 1889, Martinus Beijerinck studied yeasts able to live on lactose. He saw that lactose use depended on a specific soluble power. That power became known as lactase, an enzyme for opening milk sugar. The discovery linked a household food to the emerging science of enzymes. It also showed industry where to look, not only animals, but microbes. Dairy cellars and whey streams held organisms already fluent in lactose. Through the 20th century, researchers searched those organisms with patient care. Yeasts from dairy environments became important sources for milk and whey. Fungi offered other lactases suited to more acidic foods and drinks. Together, these discoveries turned lactase from curiosity into practical help. By mid-century, lactose intolerance was described with clearer medical language. Families who avoided milk were no longer treated as simply unusual. Biology explained the difference. Adult lactase often fades while needs remain. At the same time, dairy producers faced another lactose challenge. Whey, left from cheese making, carried valuable sugar in enormous volume. If unused, that sugar could become waste instead of nourishment. Lactase offered a gentler path, opening lactose without harsh treatment. Industrial interest grew where nutrition, comfort, and waste reduction met. The old microbial clue became a bridge between science and daily life. Under the microscope, the action is intimate and almost tender. A lactose molecule drifts through water, bumping among proteins and minerals. Lactase holds a pocket shaped for that particular two-sugar form. When lactose settles in, the enzyme bends it into readiness. Water joins the moment, and the central bond gives way. One molecule becomes glucose and galactose, both easier for the body to absorb. Then lactase releases them and remains ready for another quiet meeting. Nothing loud happens. The milk simply becomes more accessible. In kitchens, this change lets many people return to familiar cups. Milk can taste naturally sweeter because smaller sugars meet the tongue directly. Yogurt, ice cream, and soft dairy desserts can become smoother. In bakeries and cafes, lactase helps dairy blend into daily rituals. In dairies, it can help maintain texture as products are chilled. It can reduce unwanted crystallization in frozen and concentrated dairy foods. Beyond the table, lactase helps make better use of whey. Opened lactose can feed fermentations that create useful ingredients and flavors. It can support animal nutrition, where young digestive systems need help. And it helps turn side streams into products rather than burdens. This is the larger promise hidden inside lactase's small work. Enzymes do not conquer materials, they persuade bonds to change. They can replace heat, waste, and force with patience and precision. For milk sugar, that patience began in infants, microbes, and whey. It passed through 19th-century benches into modern dairies and homes. Today, lactase belongs to a wider movement toward careful, sustainable biochemistry. It reminds us that abundance becomes useful when waste is reimagined. Its future may be measured in cleaner streams and fuller shared nourishment. At Enzymes Bio, scientists and enzyme enthusiasts work to make this biology easy to reach. One platform, many enzymes, no tangled procurement for research labs and growing businesses. A green technology with a long future. Learn more at enzymes.bio.